We have that. Let me make it a little bit bigger so we can read the screen. That's looking good. All right, so yeah, what I'm going to be going through this afternoon to start the data mining session is just an introduction to Scikit-Learn. So this is going to be, we've been having a lot of kind of theoretical and philosophical discussions. This is going to be very, very untheoretical and unphilosophical, but very practical. So essentially what I want to do in the next hour plus is give you an introduction to machine learning. You know, this is a term or a phrase that you hear thrown around all the time. And, most people have some idea that machine learning is important and some sort of powerful technique, but I have no idea what it is. So we're going to talk about what machine learning is, and then also practically how you can do machine learning, how you can try out these algorithms with this package called Scikit-Learn, which is the Scikit. In the Python world, Scikit is something that's sort of an add-on to SciPy. That was decided 5 years ago, something like that. So there's a lot of different Scikits. There's Scikit Signal, there's Scikit Image, Scikit-Learn, Scikit whatever. So these are add-ons to the SciPy functionality, and Scikit-Learn is just the one that has to do with machine learning. So I have a link right here, and this is actually the Scikit-Learn website. And it's fun to poke around. There's a lot of different things that you can do here. They have an intro to some of the machine learning algorithms, the classes of machine learning algorithms, and then there's things on model selection, pre-processing. So if you're curious, you can go there and take a look. But I'll be walking through a few of these things in this notebook, Scikit-Learn intro. So just the outline, like I said, the main goal is to introduce central concepts of machine learning, what machine learning is, and practically how you can start doing machine learning using this package. And so we'll go through the definition of machine learning. We'll talk about data representations. This is pretty important. How do you take whatever data is out there in the world and go and turn it into bits and bytes that Scikit-Learn can use. I'll do an introduction to the Scikit-Learn API. How it's a really nicely designed and regular API for machine learning. So once you have it down, once you've figured out how to use it, you can basically use any of the algorithms in the package. And all it requires is dropping in different class names. And then we'll go into the basics of machine learning. And machine learning is kind of divided into these two categories, supervised and unsupervised. And we'll talk about what those mean. We'll talk about the two main classes of supervised learning, which are classification and regression. And then a few of the main classes of unsupervised learning, which are dimensionality, reduction, and clustering. Now, when we say data mining, this section is labeled data mining. One of the things that I think of as data mining is unsupervised machine learning. It's a way of figuring out what your data is telling you without having to put too many assumptions into it. So we'll see that. And then at the end, we'll talk a bit about model validation, so how to figure out if your model is doing well. And then at the end, I'll show you a little application which is interesting, actually, classifying handwritten digits. So given a sample of someone's writing, can you tell what digit they're writing? Whether it's a 1 or a 4 or a 9. And we'll see how to do that with Scikit-Learn. So not a lot of specific astronomy stuff today. This is just sort of kind of the introduction to the package, the introduction to machine learning in general. And from this, we're gonna jump off tomorrow and get a little more in-depth on some of these things. So tomorrow, I'll talk about, in the morning, supervised learning, and look at a couple supervised learning methods, how they work, what sort of insights you can gain from them. And in tomorrow morning's breakout session, we're going to use supervised learning to do some things like photometric redshift, to do some things like, what was the other problem I did? Oh yeah, photometric recognition of variable stars, and things like that. So that'll be the astronomy application tomorrow morning. And then in the afternoon tomorrow, we'll talk about unsupervised learning in depth and look at a couple unsupervised learning algorithms. And again, in the breakout, we'll apply those to some real astronomical data and see if we can get some interesting insights using these methods. So, any questions there about the outline of today and tomorrow? Does that sound okay? You all right with it? Good. Okay, so let's talk about Scikit-Learn. So I mentioned that it's this Python, this Scikit, this Python package add-on to SciPy. And the goal of Scikit-Learn is to give access to well-known machine learning algorithms. So everything you find in Scikit-Learn is something that's been known in the computer science community for 10, 15 years, and it's well used and well understood. The bleeding edge, state-of-the-art, cutting-edge algorithms aren't really in there because that's not one of the goals of the package. A big piece of it, too, like I mentioned, is that there's a clean, well-thought-out API. And this has been kind of cool because the API of Scikit-Learn, the way to call these estimators and to do this analysis, has started to be adopted by other packages. So, for example, if any of you know Josh Bloom at Berkeley, he started this company called Wise.io, Wise.io. And what they do is they provide machine learning as a service. And they have Python wrappers for their machine learning implementations, and the Python wrappers use the Scikit-Learn API just as sort of a standard. So, and often when I write reusable code for astronomy, I'll use the Scikit-Learn API to make the estimators available. Scikit-Learn is built on NumPy, which is as you know, is the numerical computing, kind of the package that gives you data buffers and data arrays, and SciPy, which is the package that wraps all sorts of useful Fortran codes to do interesting scientific things. And the last thing I should mention is that Scikit-Learn is not really designed for big data. So people like to do machine learning on big data because those are buzzwords that get you jobs. And Scikit-Learn can't really do that. It's designed for small to medium data sets, though there is some work on extending it and doing some more interesting large data sets out of core, that kind of thing. But I usually think about Scikit-Learn as something that I use for teaching, for doing kind of day-to-day small problems, and for gaining insights about the algorithms, but you may have to go to more specialized packages if you're trying to, like run something on the entire LSST data set or something like that. But that's a different challenge.
What's your description of big data, like orders of magnitude?
Oh, so in this, when I say big data here, I'm thinking anything that doesn't fit in memory on your MacBook Pro. Right, so anytime you have to start worrying about where your data is living and having maybe different cores communicating with each other and data living on different machines, that's where Scikit-Learn sort of breaks down. Thanks. Okay, so let's ask a question. What is machine learning? And this is actually, machine learning to me just seems like it sounds more complicated than it is. But basically, machine learning is about building programs with tunable parameters. And these parameters are usually just arrays of floating point values. And these parameters are adjusted automatically so that the machine learning algorithm, by looking at some training data, can tell you some information about some new data. Now, if you think back to the last couple days, you might think to yourself, like, what's the difference between this and just doing a maximum likelihood estimate, right? Like fitting a line to data, and then that line tells you about new data. The answer is there's no difference. Machine learning is just maximum likelihood estimation. And you define a model, you fit it to data, and then the model tells you about new data. So there's nothing new here that we haven't done yet. But the reason it's called machine learning is, actually I don't know why it's called machine learning, it's just model fitting. So what we're going to do, we have this introduction to machine learning. It's just an introduction to how to do model fitting in practice, how to use code to fit models to your data and learn things about new data. And we'll see some examples of that. So here's an example of, quick example of a classification algorithm. And this is one that we'll go through tomorrow. This is a little bit hard to see. Let me make it a bit bigger. So the classification algorithm, we have this two-dimensional data, and there's a group of points that are up on top, and there's a group of points at the bottom, and they have different labels, right? We have blue points on top, and we have red points or brownish points on the bottom. And a classification task might be to say, I want to draw a dividing line between these two groups of points. And so this is the dividing line that the algorithm came up with that divides those two groups of points. And now, so that's the model we fit to the data, right? And now what you can do is say, if I add another point to this plot, I'll be able to tell you based on that model whether it should be red or whether it should be blue, right? So this might be, for example, the G minus R color, and that might be the U minus G color. And then on the top, you have main sequence stars, and on the bottom, you have R Lyrae stars that you know from their periods. And then you go and observe a new star, you plop it down on that diagram, and you want to know whether it's main sequence or R Lyrae, and you figure out the result, right? That's exactly what we'll be doing with this later on. So that's machine learning. That's a classification algorithm. We're trying to classify these discrete labels of sources. And you might think to yourself, like, this is a little bit ridiculous, right? Like, that's all machine learning is? Like, I could do that when I was a kindergartner. I could draw, right? So the thing about machine learning that makes it powerful, though, is that even though we're just looking in 2 dimensions here, we could do this in an arbitrary number of dimensions, right? So you can plot 2-dimensional data and do this. But imagine if you had 1,000-dimensional data, right? If you look at a spectrum is basically, a single spectrum is a point in 1,000 dimensions. First dimension is the magnitude of the first bin, and the second bin, and the third bin. And instead of plotting it as a line on a piece of paper, you could plot it as a point in 1,000-dimensional space. And these algorithms, these machine learning algorithms, will generalize up to lots of dimensions. So, if you plot 1,000-dimensional data, it might be hard for you to draw by eye a 999-dimensional hyperplane that splits those. But this algorithm can do that just as easily as it does it in 2 dimensions. So that's where the power comes in. So that's a classification task. Just in case you wanted to see that, I'm not just drawing something here, I'm actually doing an algorithm. You can load this code here. This is the function that I ran. And you can look through here, and I'm actually creating data and doing a classification and then plotting the results. So it's a real result that you can look at if you like. Another type of machine learning task is a regression algorithm. And this looks familiar, right? We have data and we're fitting a line to it. And the context here is that regression is rather than predicting discrete labels, red or blue, star or quasar, main sequence or R Lyrae, in regression we're predicting a continuous variable. So what we have here is we have a bunch of points that we know the x value and we know the y value, and we want to say, well, given an x value, can we predict what the y value might be? So we need a model that given x predicts y. And what we've done here is we've fit a line to the data. So this is exactly what we did on Monday, right? We fit a line to data. You know how to do this. You write the likelihood, or the cost function or whatever. You minimize the cost function and you get the result out. And so now the point is that if you add another observation here, another x value, you can predict from this model what the y value might be. So an example of this in astronomy is something like maybe photometric redshifts. So the x value here would be the photometric colors, U minus G or something like that. And the y value would be the redshift. So given some training samples for which you have spectra, you can define the model. And then given some new observations for which you don't have spectra, you can predict what the redshift would be. So regression, when you see regression, that's something that's predicting a continuous variable, where classification is predicting a discrete variable. And just like before, you might say, well, I did this in my kindergarten statistics class. I drew a line through data. And it's easy in 2 dimensions. But now imagine again if instead of having just one x, you measure 1,000 different x values. You measure 1,000 different features for these things that you're trying to predict. And you still want to predict what the y is. You want to predict some continuous variable. That's difficult to do just by eye, by plotting the data. But these algorithms generalize up to higher dimensions, and you can do these more sophisticated problems. So that's machine learning in a nutshell. You're fitting models to data, and the models generalize the new. So the first thing you need to do is figure out how to get your data into a form that Scikit-Learn can use. So this is the data representation question. And data in Scikit-Learn, I'm going to make use of this. I know I told you I wouldn't make use of this, but I just like drawing. So data in Scikit-Learn is, it comes in a matrix. So think of a two-dimensional matrix right here. And each row of the matrix is one sample. And each column of the matrix is one feature. Now, what do I mean by samples and features? So, a sample is something that it's an object that you're interested in. So, an object would be like a galaxy, or a star, or we'll see later, a flower, or anything you're observing. The sample is the actual object that you're interested in. And the feature is the measurement you have about it. So a feature might be the U minus G color, or the feature might be the degree of twistiness in the spiral arms that you somehow measure. Or the feature might be the length of the flower petal that you're looking at, right? So the data is in this matrix that's usually called big X. And the size of the matrix is the number of samples, n underscore samples, by n underscore features. So this is our X array that gives all the features of the data. And then if we have labeled data for supervised learning, the next thing that we have is basically a vector. This is y. This is a one-dimensional vector, and the y vector contains the labels. So in this case, the labels for classification, what we saw before, this might be red, blue, red, red, blue, red, blue. But you don't actually put the string red or blue in there, you'll just use some number, like 1, 0, 1, 0, 0, 1. So these are numerical code that represents the labels that you're looking at. So just to make this more concrete, right? If you're looking at galaxies and you're trying to classify, like, say you want to classify the Hubble. Let's do a regression problem. Say you want to classify the photometric redshift of galaxies. You have a bunch of galaxies here where each row tells you one galaxy. Each column tells you some photometry color, G minus R, U minus G, R minus I, whatever, for each of these galaxies. And then the labels here would be the redshift of each galaxy. So the first redshift corresponding to the first row, second redshift corresponding to the second row, etc. So that's how you make your data. And one thing you'll notice in that is that because you have this in a matrix here, you need to make sure that for each of your samples, you have the same type of observations, right? Machine learning, in the way Scikit-Learn is created, machine learning won't work if for one galaxy you just measured the U-band, and the next galaxy you measure how twisty the spiral arm is, and the third galaxy you measure, the absolute brightness or something like that. You need uniform measurements for each one. You need to have the same data about each of the different objects. That can be relaxed and kind of in more advanced applications, but for basic machine learning, that's what you need. You need the same measurement for each of your objects. So this is what I've said right here. You have n samples, which is the number of samples, number of objects you have, number of individual things you care about. And n features is the number of features or the number of distinct measurements you have for each sample. And your matrix is number of samples by number of features. And I should have written here that the length of y is number of samples. Because you have you have one label here for each of your rows of your matrix. Yeah.
How independent should the features be among themselves?
The question is, how independent should the features be? It doesn't really matter. You can do anything, but for each individual algorithm, it might perform better or worse. But that for the overarching, just how to get things in there, it can be anything you want. Yeah.
Why do you distinguish the features from the labels? It seems to me like you could put the labels as another feature. Why do you do that?
Yeah, the reason you distinguish between the features and the labels is because generally the labels are something you only have for your training set. So for photometric redshifts, you have a certain collection of galaxies for which there are labels. And then the labels are things that, given another set of features for unknown objects you can predict. So we get these features for a new set of galaxies, and then we can predict what the label is, predict what the redshift is.
So ultimately, that's the thing that you want to get out.
Yeah.
You're telling it, listen, I know this one, so you should get this.
Yeah, so the labels are you can think of them also as unknowns. At first, for your training sample, they're known, but then for the rest, they're unknown.
So the label is the thing that allows you to the classification. That's what
Yeah.
label means.
The label is the thing you're interested in predicting. Yeah. Thanks. Other question? Yeah.
Do you need a value for every feature? I mean, do you have a sample with certain math?
Yeah, that's a good question. The question is whether you can be missing features and
samples, so it's supposed to.
So for the most basic algorithms, for the kind of level 1 machine learning, you need all this data to be in here. You can't have any missing features. If you go to more advanced algorithms and more advanced approaches to the algorithms, you can relax that a little bit. But in general, and the things we're going to be looking at today and tomorrow, we're going to have no missing data. So missing data is actually a pretty complex question. Any other questions? Oh, one more.
Yeah, so how does the performance of the method depend on the size of the data set?
So the question is, how does the performance depend on the size? And that completely depends on the method. So there's some that scale really quickly with large data sets, some that are really slow. And we'll get into that a little more tomorrow, I think, when we talk about those in detail. All right, so let's look at a simple example. And this, if you've ever studied machine learning, or if you've ever done anything along these, for some reason, the first example that everyone uses is this iris data set. And just to conform to everyone else, I'm going to use the iris data set as an example. So in this case, you can think about the iris data set. This is a botanist went out into the woods and wanted to take a look at some irises and ask if he could figure out what species the iris is. So they had 3 different species of irises in this particular woods. One was the iris setosa, which looks like that. One was iris versicolor, which looks like that. And one was iris virginica, which looks like that, right? So now you have these 3 different types of irises. You want to classify what kind of species they are. So in this case, what does the number of samples refer to? In this case, we're not going to do anything that sophisticated. What we're going to do is look at the iris data set and that's loaded into Scikit-Learn. And the features we're using are the length of the sepal, width of the sepal, length of the petal, width of the petal. And then we have our 3 target labels, which are these 3 iris classes. They're 3 species names. Yeah, this is the biology thing. And the big guys are the petals, and the little guys are the sepals. Yeah. Yes?
Sorry, Jack. Are we learning from these images, or do we have somebody go out and measure the plants?
Yeah, fortunately, someone has gone out and measured the plants. So these are just examples of what they look like. In the data set we have is some botanist who actually went out into the woods with his ruler and started measuring things and writing it down. So because this is kind of a standard data set, this is one of the data sets that Scikit-Learn has available, and you can just say, I want to load the iris data. And this is, we'll see in a second, but Scikit-Learn has a lot of data sets that you can play around with, and it's really helpful for demoing things and just for exploring different algorithms. The keys in here, this tells us which, oops, I want to make that smaller, so can you guys read that, or should I make it bigger again? That's fine, okay. So the keys in here are the things that are part of this data set. We have the target names, which are the names of the species, the data, the feature names, the target. So let's take a look at this. If we look at the iris.data, we can ask what the shape is. And remember, I told you the shape is number of samples by number of features. So we print that out, and we see that we have 150 samples by 4 features. Right, so that's 150 different flowers, and for each flower we have 4 measurements. And just to take a look at the first row of this data, the petal length is 5.1 centimeters, the width is 3.5, the sepal length is 1.4, and the width is 0.2. So that's our data. This is for the purposes of the algorithm, this is everything we know about that iris. All right? And if we compare this, we have the iris data shape and the target shape. Data shape is 150 by 4, so that's that X matrix that I wrote right there. And the target shape is 150, so that's that Y vector that I wrote. And to take a look at these targets, it's just a bunch of zeros, ones, and twos, right? This 0 is one species, 1 is another species, 2 is another species. And this is, the target names gives you the kind of dictionary of how to interpret that. So all the zeros are iris setosa, all the 1s are versicolor, and all the 2s are virginica. So this is our data. We've distilled the real world of messy flowers down into one nice little data set that's numerical and regular and square and matches and everything like that. So this is, actually I should say right now, this process right here is called feature engineering. You know, you take the messy real world and you turn it into something clean that your algorithm can use. And feature engineering is the most difficult part of doing machine learning and doing statistics in general, right? You have to figure out what numbers to put into your algorithm, and that's where all of your expertise in your own area of astronomy is really vital, because you want to know exactly how to pull data out of the real world. Yeah. Do you? So the question is, can you look for features automatically? I mean, you can. There are ways to, given a list of possible features, there are ways to figure out which ones are most useful to learn the feature importances. But you really need to use some human insight to figure out what those possible features are, right? Like, I don't know of any machine learning algorithm who could take the raw output of Gaia and tell you, well, this is something interesting about the universe, right? You need a human to look at that data and figure out what to plug into the algorithm. I don't know. Maybe that's the next thing. Like, we need IBM Watson to tell us what the features are or something. But yeah, so machine learning is not a magic bullet. It's just a way of, it's a class of methods that help you look at your data. Any other questions on that? Yeah. So you could do things, and given some features, I want to say more on that. Given some features, like for example, if you just plugged in the pixel values of this image, you could do a machine learning algorithm on it that would say, oh, here are some interesting features in the image. Here's some interesting aspects of the image that might correlate with the real world. But still, you're telling it the features are these pixels. And that's what you're working on. So features have to be some sort of regular data. Yeah.
So it's important that the number of labels is equally distributed, or more or less equally distributed among the different classes?
Okay, so the question is whether the labels have to be equally distributed, like balanced numbers in each class. And that's one of those things that depends on the algorithm. Some are better with balanced, and some are better with Some can handle imbalanced features, and that's one of the things you have to understand about your model when you apply it.
When you consider individual pixel values as a feature, does it do any sort of realignment which might suggest that one pixel is really better
Yeah, so the question is when you use pixel values as a feature, is there any sort of realignment that happens to kind of say that this part of the image is the flower and the other part is the background? Maybe that's another thing that's difficult. You know, if I had an iris that was a thumbnail with 100 pixels versus a high-resolution image with 1,000,000 pixels, like you can't really put that in the matrix, right? You can't have a row of 1,000,000 followed by a row of 100. So
one case the iris was on the left and the other the iris was on the
yeah.
right.
That's the other question. So if the iris is on the left versus the right and the pixels don't line up, in that case you want to do some feature engineering. So you have in your head, you know that kind of this is the iris, this is the interesting part of the image, that's the interesting part of the image. You can do that by hand, by cropping the image and redoing it. There are also image processing techniques that are really nice for feature extraction. So you could do something like define a filter on your image that would actually find the interesting piece, and that's what's done in practice. So, like you load your picture of your friends exploring Madrid onto Facebook, and Facebook has this feature extraction thing that finds the human faces and boxes them, and then runs those human faces through some sort of trained classifier, and then says, do you want to tag Andy or whatever on the picture, right? So that's all those layers that are going on, right? Is that clear, all that? Yeah. Features and inputs and everything. Okay, so we have all of this, and now let's one of the things that's useful when you get a data set like this is just to visualize it, so kind of see what's going on here. So this is, I'm plotting the x-index versus the y-index, so this is sepal width versus sepal length. That's kind of nice. Let's see something else. Sepal width versus petal width, or sepal length versus petal length. You start to see, oh, this is interesting. This class is kind of all off by itself in this projection. And these are pretty well separated. There's something going on. You can imagine maybe drawing a line right here to separate those two, and a line right here to separate the rest. Let's take a look at the petal, the width versus the width. You see the same sort of thing here. So this is the data exploration. Once you get data, it's useful just to plot a few views of it and see what it looks like, just to understand what's there. And if you did this and you saw that one of the sepal widths was 5 kilometers, you would say, oh, my data needs to be cleaned up. That's obviously a bad value, or a really, really interesting flower. And this right here is kind of a rudimentary form of dimensionality reduction, right? We're taking 4-dimensional data and we're projecting it down to 2 dimensions to explore what the data looks like. And we'll see a little bit later a way to do dimensionality reduction automatically. So instead of just saying x versus y, 2 versus 3, we'll have an algorithm that will learn from the data what might be the most interesting projection to look at. That's an example of an unsupervised algorithm. So, I just did this quick exercise. Good job.